Dr. Ovet, and I'll be talking about making use of negative data from semi-supervised learning for image classification. So this project is based on a paper titled One-Bit Supervision for Image Classification by Hang-Tong Hu et al., and you can find it in NeurIPS Proceedings 2020. So first, there are two types of supervision, right? The usual supervision that we know, full supervision, so we give someone a collection of images, and one by one, image by image, they look at the possible labels and assign an appropriate label to that image. This is compared to one-bit supervision, where we give a person an image and a label, and they simply say yes or no for whether the label and image match or they do not. So the authors of the paper make use of both of these types of supervision in their paper, and it can be best described by this graphic, which can be found in their paper. So think of so these points here on the left are all of our images. So it's all of our data. We take a small subset of those and fully label them, so full supervision. And we train a neural network on that small subset of the data. And then we want to take some random subset of the remaining data points and input them into that neural network. So the neural network will give us some predicted labels. We then give those images and predicted labels to a human and ask them, yes or no, do these match? So we'll get some positively labeled images in red and negatively labeled ones in green. Now the positively labeled ones become a part of that fully labeled set, which we can then retrain that network on and get model M1 here. And then we keep iterating that process. Every iteration they call a stage. And notice here, the negatively labeled data is just hanging out, not being made use of. But the authors actually do make use of that negative data. So first, I want to mention they use the mean teacher adversarial model as their neural network. And in order to make use of the negative data, they consider the teacher's prediction, the student prediction, and the loss function when choosing the next possible label. So they suppress the incorrect label to 0 and then choose a next one. But that process is a little bit involved. So for my implementation, I simplified the algorithm, but basically did exactly as they did. So in illustrating this, it'll also help illuminate what the authors did. So suppose we have our data D, we break it up into the training set DS and the test set DU. We take a small subset of the test set, so that's like the blue triangles, and train a neural network on that set. So I used a simple convolutional neural network. And then we take another subset of the training set and input it into that trained network, and we'll get some labeled images as the output. Now to simulate this human one-bit supervision, we assume that humans have a 95% accuracy, just as in the paper, and we keep 95% of the positive and negatively labeled images, throw away the rest. And now we want to make use of the negative images, so I just took the most simple route, and the neural network, once you input an image, gives you a list of probabilities for all the labels and gives you the highest probability one. So I take the second highest probability one as the ground truth. I replace the ground truth with that label, and then train the network on that initial training set, the positive labels, and the adjusted negative labels. So that completes one stage, and then you keep doing this until you exhaust all of your data, and then you can test it on that test set. So I applied this algorithm to CIFAR 10, and the results that you're seeing here, the orange line represents 4 stages, the blue line represents 5 stages, and the green line represents 6 stages. We can see here that with 4 stages, we got the best accuracy, although it did take the most time to run the algorithm with 4 stages. And the reason this isn't surprising is because the smaller the number of stages, the larger the number of images in that initial training set. So the better the initial training set, the better start that the model has. And here I compared it to training the network on the full set of images, which isn't really a fair comparison because these are two completely different situations, right? in the situation where we can fully label the entire training set, that's going to potentially be very expensive, whereas this algorithm is meant to be for a situation where we don't have that much time or resources to fully label a huge data set. We want to get away with fully labeling a small amount of the data and then making it easier to label some of the rest of that data. And then when applied to CIFAR 100, we got the same exact result.